Good evening, ladies and gentlemen. Thank you very much for providing me this opportunity to present my work in this learned forum. I am Shabbir Abbasi. I'm a PhD student at Victoria University of Wellington, New Zealand. The topic of my presentation is particle swarm optimization, a wrapper-based feature selection method for ransomware detection and classification. Before starting the presentation, I want to give you the overview of my presentation, beginning with the introduction of the problem. I'll walk you through the background, where I will discuss some existing literature on the topic, and also I will discuss a baseline method, which we assume an existing method that we have considered as a baseline of our experiments. Then I will present the proposed method in detail. Afterwards, I will present the results and the experiment conducted with our method. And finally, I'll conclude my presentation with the suggestion for future work. And then I will open the floor for the questions. I start with the introduction of the problem. Ransomware. Ransomware is a type of malware that hijacks users' data, usually by means of encryption, and render it useless, hold it hostage for the ransom. The number of indiscriminate and targeted ransomware attacks have been growing for a couple of previous years. Ransomware is one of the modern malware that has high financial damage rate. McAfee Lab reported 118% increase in ransomware attacks in the first quarter of 2019. The financial damage reported by SonicWall in the first half of 2019 is $110.9 million US, which is 15% more than that of 2018. Take an example of ransomware attack on Baltimore City in May 2019, where President City Council called for federal emergency to deal with it. The cost of the recovery of the system was more than 18 million US dollars. To further galvanize the problem, consider the ransomware attack on Hancock Hospital systems, where hospital administration opted to pay ransom despite of available backups, considering the cost of recovery in terms of time, money, and human lives. To prepare the remedy of a malware is generally analyzed for its various static and dynamic patterns. Generally, there are two approaches to malware analysis. Number one is static analysis, and the other is dynamic analysis. In static analysis, a malware is analyzed to learn various static patterns of the malware or various static attributes of the malware like string signature, byte sequence, etc. Whereas in dynamic analysis, a malware is executed in a controlled environment to learn its various its runtime behavior with operating system and other machine resources. And that is why dynamic analysis-based detection approaches of malware are known as behavior-based detection of malware approaches. Anti-malware evasion techniques like code obfuscation and polymorphism render static analysis-based techniques useless. So in this sort of situation, for the modern malware like ransomware, behavior-based detection approaches are used to complement the process of detection. But behavior analysis of malware produces high-dimensional data that can be grouped into various features. But fortunately, we have the solution of high dimensionality in terms of dimensionality reduction techniques. In this section, I will first present some of the existing work in this domain, and then I will present an existing method which we considered as the baseline method for our experiments. On this slide, so I just listed down some of the existing work and the various tools and techniques that have been used for analysis and detection. So by going through this, we can find out that mainly the techniques for the mechanism for detection of ransomware was used as data monitoring and event monitoring. It is worth mentioning here that the core behavior of the ransomware is file encryption. File encryption is a benign activity, but that have been used as a malicious purposes, and that is why an antivirus tool is unable to catch that benign activity. So a benign activity is being used for the malicious purposes, and that is the main glitch. And that is why most of the detection techniques revolve around data monitoring, because everything ransomware does is all about the data. Here is an existing method presented by Sagendra et al. This method we considered as the baseline. So in this diagram, you can see that there are two parts. One is the analysis part and the other is the detection part. In the analysis part, the sample of ransomware and goodware are analyzed on a virtual environment, that is on a Cuckoo sandbox, to learn it to analyze its runtime behavior with the operating system. By doing that, various features are actually extracted, and those features are grouped into multiple groups. So these groups are can be seen as the API invocation here, registry keys. So this is another group, file directory keys, and so on. So that there can be many groups. So this data is passed and then passed to the detection module. In detection, the author performed a feature selection approach because these features are more than 30,000 features. So they resorted to the feature selection method, and they used mutual information as the feature selection criteria. And they selected 400 top ranking features which they put into a regularized logistic regression classifier to classify into goodware and ransomware. The selection of 400 features was justified by scaling the selection from 100 to 1500 features. And 400 features were reported to be producing averagely better results with this. So from the baseline method, we can see that selecting all the features using mutual information and without ignoring the feature groups within that feature set, and selecting the features from all of the data, ignoring those groups, ignoring the effectiveness of those groups for the ransomware detection, can be used to improve the performance of a detection system. So considering this, we formed our hypothesis, which is the effectiveness of various features. Considering the effectiveness of various feature groups, classification performance may be improved if the feature selection is performed by considering each of the feature group. So we proposed a PSO-based wrapper method of feature selection to address this problem. So this is the big picture of our method. We can see that our method contains two stages of feature selection, which is referred as stage 1, and stage 2, which is actually utilize particle swarm optimization in it. The details of both of these stages I will be presenting in the upcoming slides. We start with splitting the data into training and testing set to avoid any feature selection bias to be introduced in our process. So the training data is then proceeded to stage 1, and the training data is transformed at the stage 1, and the transformed data is forwarded to stage 2. Also, it is forwarded to final transformation stage. So the transformed data forwarded to stage 2. PSO produces the best particle using that data set, and that best particle is the output of the stage 2. This particle is then forwarded to the final stage of the transformation. So at the final stage of the transformation, the data obtained from the stage 1, the transformed data obtained from the stage 1, and the best particle obtained from the stage 2 is used to transform the data, and the training data is then used to train a classifier, and the test data in the same way after transformation is used to evaluate the results. So this is stage one. So I want to show that. So now I want to, I will be explaining the stage one here. So in this stage one, as I have already mentioned, that the features in our data set can be grouped into various features. So suppose we have M features in the data set. So all these M features have various number of features within those. So there can be a huge difference between even within the groups. Like group 1 may contain thousands of features, whereas group 2 can contain only 100 features or 200 features in it. So what our stage 1 does, stage 1 actually selects an equal number of features from each of the group. Like it considers the feature group, and considering every group, it selects equal number of features on the basis of mutual information, and on this basis it transforms the data. Like the output of the stage 1 is a transformed data with all these groups with equal number of features, which we have mentioned as X features in here. So the main aim of doing this is that if we go for the wrapper-based method on the whole set of data, which has a huge number of feature groups, so it will be very expensive. So at the first stage, the aim of introducing this stage is to eliminate the difference between the number of features in each group. And also it will reduce the computational cost at the second stage. Now I move to second stage. The second stage implements PSO. Before going into details of the particle swarm optimization at the second stage, I would like to introduce the particle here. The particle in our representation is a vector of M values. So these M values correspond to M feature groups. So every R value corresponds to its ith feature group. So R1 corresponds to first feature group in the data set, and Rm corresponds to mth feature group in the data set. R is a continuous number between 0 and 1. Now I move to proposed method stage 2. Okay, so at stage 2, we can see that the transform data at stage 1, I hope you can see the mouse. The transform data at the stage 1 is forwarded to the stage 2, which implements particle swarm optimization, and the output of this stage is the best particle. So what is happening inside the particle swarm optimization? We used it to optimize the process of selection of features from each of the group. So PSO generates a population of particles, which is forwarded to the fitness function. Within the fitness function, we once again split the data into subtrain and subtest data. The subtrain data is forwarded to transformation of the data within the fitness function. So the particle generated by PSO governs this transformation. We translate this R value into a K value, which is a constant number, in a way that Ki is equal to Ri multiplied by X, which is actually that if we are dealing with the ith group, ith feature group, so from the X number of features of the ith group, because X is the total number of the features, we take only R number of features. We will multiply it with R and convert it into a constant number, which is K. And then we select K features from the ith feature group. In this way, from all of the feature groups, we select Ki number of features. We transform the data on the training set, which is then forwarded to the wrapper classifier to train the wrapper classifier. And similarly, the subtest data is transformed and used to evaluate the fitness value. The best particle from the stage 2 is the output of this stage. The fitness function in our case is error rate. We utilized balanced accuracy, as with our data set, there was a huge difference between the number of goodware and ransomware. So we utilized balanced accuracy to calculate the error rate. In this section, I will be presenting the experiment we conducted in this regard and discuss the results. So I start with the data set. We use an existing data set presented by the same author who presented the baseline method. The data set contained 582 samples of ransomware from 11 different families and 942 samples of goodware. The details of these samples can be seen in the table given on this slide. It is worth mentioning here that finding a data set matching with our objective was not easy, because ransomware is a modern malware, and the behavior analysis of ransomware is a risky and time-consuming job. So we resorted with this data set to continue our experimentation. So this is some details of this data. So the samples of the malware and goodware were analyzed for 20 seconds in the Cuckoo sandbox, and 30,967 features were extracted from that. What is a feature? A feature is an operation performed by a malware or a goodware with the operating system. So that is called, that we call a feature. So these features can be grouped into 7 different groups. And these groups can be seen as API was the API invocation, drop was the extension of the drop files, and the number of features can be seen in the front of the every feature group given in the table. So in total, there were 7 feature groups. So on this slide, I will be mentioning the evolutionary parameter settings we used. We used some recommended settings of evolutionary parameters, which were recommended by the Eberhard, the founding father of the particle swarm optimization. We ran our experiment for 30 iterations with 100 epochs each, and kept the swarm size as 30. The value of inertia was used as 0.729844, whereas cognitive and social parameters were kept as 1.149618. Okay, so on this slide, the details of the classification algorithms we used as given. We were consistent with regularized logistic regression as the wrapper classifier. All of our experiments, all the experiments we run was using the same wrapper classifier, which is regularized logistic regression. And we didn't perform any sort of tuning of the classification algorithms. However, we used other classification algorithms like random forest, decision tree, support vector machine to generalize the results of our method. And finally, we used regular logistic regression with baseline settings, like because the baseline method was also using the same classifier, and one of the instance which we named as the baseline was used with the parameters tuned with the baseline settings. Here are the results of our experiment. So as I have already mentioned, that we ran our experiment for 30 iterations for 100 with 100 epochs each. In this table, you can see the results of the baseline method and the classification algorithm given here, and the proposed method at stage 1 and stage 2. We calculated the results also at stage 1 and then finally at the stage 2, but we consider stage 2 as the final result. To calculate the results of the baseline method, we used a four-fold split of the data, four-fold cross-validation, and the results of the baseline method are the average results of all 4 folds. For the proposed method, we ran PSO for 30 times for all 4 folds, and the results reported here are the average results of these all 4 folds. For significance, we performed one sample two-tailed t-test with a confidence interval of 95%, to calculate the significance of the results. The results at the stage 2 in red represents significantly poorer results than the baseline, and the results in green represents no significant difference, whereas the results in blue represents significantly better results. We can see that with the baseline classifier, the baseline method was giving only 97.20%, whereas in the proposed method, it was 97.34. Sorry, I cannot see the results. Okay, 97.34 with a standard deviation of 0.11%. These are the results of the binary results. We can see that our method presents comparable results with the baseline method. Whereas for multi-class classification, our method performs better than the baseline method, although there is still room for the improvement. Like the baseline method with RLR was giving 52% only, whereas our method was giving 54.61% with a standard deviation of 0.44. And similarly, in the case of support vector machine, it was 52.85, whereas with our method it was 54.57 with a standard deviation of 0.47. Okay, so for our results and experiments, we perform analysis in 2 dimensions. Number one is that in terms of convergence of the algorithm, and the number 2 is the feature selection from each of the feature group and how our method performed a bit better than the baseline method. It was selecting different features because we use PSO in a way to select different features from different groups. So here is the convergence graph of our algorithm. This one is for the binary and this one is the multi-class. We can see that our method performs exploration for the first 20 to 30 epochs, whereas for the rest of the epochs, it performs exploitation. The whiskers in the graph shows that our method is stable among various runs. The second dimension of our analysis is the number of features selected from each of the feature group. So this is for the binary class classification. The proposed method is shown in the green, whereas the baseline method is in the brown. We can see how the proposed method selects various number of features from various feature groups. The baseline method was selecting most of the feature from red group, which were 48.06% of the features were fetched from this group, whereas our method was fetching only 18.34% of the groups. And it was, taking 22.31% of the feature groups from the API class, and the rest of the combination of the selection of the feature from the rest of the group can be seen from the method, from the graph. Similarly, for the multi-class classification, we can see the selection of the feature selected from various number of from various feature groups, and we can see clearly that how our method fetches fetch a feature from considering the effectiveness of features and trying to get the optimal number of features from those groups to get the best results.
I'm sorry, Muhammad. Remember that you already spent your 20 minutes slot, so
okay,
try to
I'm just
finish.
concluding it. I'm just concluding it.
Okay, no problem.
Okay. So with the conclusion, we presented a new feature selection behavior-based ransomware detection method. The proposed method is stable among various runs, gives significantly better results for multi-class classification, and produces comparative results in binary class classification. So in future, we are considering that the sequence of operations should be considered while doing the analysis and preparing the data set. Inclusion of more feature groups can be effective for the accuracy, as we can see that there is enough room for multi-class classification. Also, the time of analysis, which was 20 seconds for the data set, can be further increased. So it's up to you now. I would appreciate if you have any questions. Thank you very much.
Okay, thank you very much. I told you that to finish because I said you were in slide 27 of 48, and I thought you have another 20 slides. But
Sorry for that.
but you finish on time, so that's great. That's great. So, any questions you can ask by raising your hand with the app or asking directly in the chat. Okay, Hossam is asking. Hossam is saying, is your dataset balanced? What is the distribution of the instance over the classes? I mean, malware to benign ratio.
Okay, so I will move to, once again, I will move to the dataset. Okay, so here is the detail, and we can see here that number of samples here. We were dealing with scenario like there were only 4 samples of PGP coder and 942 samples of goodware and only 582 samples. So I have mentioned already it was not actually balanced. So that is why we use 4-fold cross-validation, so that at least PGP code, 1 sample of PGP coder should be there in each of the fold.
Okay, any other questions? There is a question about Kehinde Babakba is asking, thank you for your presentation. Just wondering which feature group did you find more informative?
Well, it depends here. So from here, we can see that our method was selecting maximum number of features from API calls, from API group here. And also in case of multi-class classification, we can see the maximum number of features are fetched from not only, sorry, this is troubling. Sorry for this turbulence. Okay, so here we can see that for multi-class classification, our method was fetching most features from str group. So what was in the str group? So the different string values which we found in the memory of a malware which is running in a machine. So from the memory of the malware, all the binary we collected from the memory of the malware, it becomes some strings. And from those some strings, it also contains the encryption keys and also this sort of stuff. So for multi-class classification, our method is fetching most of the features from str group. It means that this group was valuable for multi-class classification, whereas from the for binary class classification, it was fetching most of the feature for API class.
Okay, and final question. Hossam is saying, just an idea, you can consider the feature reduction rate in your fitness function in addition to the accuracy.
Yeah, thank you very much. I will definitely consider it.
Okay, thank you very much, Muhammad. It's been a very nice presentation. Thank you guys for your questions also. Virtually clap for Muhammad. And thank you very much again.